Hello everyone. Am I audible? Okay. Yeah, okay. I think the meeting is also recorded. So we can start our session. So, hi guys. Welcome to the new cybersecurity upskill program. So, by Logic Labs. So, today we'll be starting our first session. So, from this onwards, everything will be part of the course. So, so now we'll be basically touching upon what is a computer and the architecture behind it, and later we'll be moving on to the cyber security part. Okay, so just before entering that world, I'm here just trying to get acquainted you guys with the with the basic nomenclature. So what is computer and how IT grew this much. So how this boom happened and all. So we'll be discussing these general aspects of this IT, and then the computer architecture. So how the computer architecture has been developed over the course of years. So and how the internet has been built up upon this developed infrastructure. So we'll be just uh, cruising through these topics, and then we'll be moving on to the networking concepts. So yeah, if you understand it right now, so IT, do you think IT is available only for the that whoever is using the internet purpose? Like, do you think the IT is going to be useful only for the healthcare sector, or you can, or maybe the entertainment sector only, or do you think is it helpful in the other industries also? For example, let's just say the production industry. So do you think the IT is helping those industries, or it is or it has been only uh, concentrated to certain parts of the industry? Just type any yes or no in the chat, guys. Like from here on will be a little bit more interactive, so a quick yes or no would be appreciated, because we have only very 1 hour sessions, right? So that's why. So yeah, there are so many sectors, right? For example, you can say the oil industry. So do you think the oil industry is getting benefited from the IT? Definitely, right? So for example, if you take let's just say in India, the let's just say a company A is supplying oil to the nation. So it has laid numerous gas pipelines in the country, and it is transferring all of this gas through these pipelines. So now in 2020, in this decade, what happened is everything, how to manage these gas pipelines, how to manage these, how much amount of gas that we are supplying each day by each minute. So if any a problem at any plant, at any station occurs, so let's just say this is a gas pipeline, it got an issue, something, a leakage happened. So immediately what happens? Alarms are there. So immediately alarms are triggered, right? So immediately they will notify these concerned individuals. So immediately the security authorities will come, and they will rectify this issue. So similarly, not just in oil industry, in every industry. So IT is basically everywhere. So now IT, it basically it helps to build, and also it helps to grow the commerce and the business sector. The commerce and the business sector are right now, you can say they're like dependent on the IT. They're like IT is part of these sectors, we can say. And also the time taken by these sectors to generate this business is also minimized. So just managing all of this pipeline, just going back to the same oil company this year. So for this guy, for these guys in the company A to manage the all of these pipelines, and manage all of the revenue that they are generating. Now the time that they will be doing with the help of the IT. So everything, if they just build an application, you just say, in that website, like everything is getting logged, so everything is getting journaled. So the time to review all of these items is very very less. So when time is saved and generating the business, the income will be more also. So that is also another advancements, you can say. And also on top of that, the it also supports electronic security, storage, and efficient communication. So efficient communication is also one of the most important things, how IT plays a key role in different and respective different industries. Is that clear, guys? So now coming back to the cyberspace. So now we are discussing about the internet era, right? So earlier, how the internet used to be, it used to be very centralized. So you can say like this is the server, and these are all the different computers that are connected to the server. C2, C3, C4, C5, like this. So earlier this used to work, right? But when the internet is getting more advanced, and when more number of systems are increasing, the demand, when the demand and the supply is getting like increased like exponentially. When I'm trying to add more and more computers, and the servers are limited, what happens here? Like clogging is happening, clogging, so much clogging. What happens when so much clogging happens? The server gets busy, or or it might get crashed also. The server might get crashed. So this is called basically a bottleneck, I can say. Right. And also, what happens if a server gets crashed in in a centralized environment like this? All of these computers, they get disconnected. They get disconnected from the internet. So it's not distributed enough, right? It's only centralized over a single point. So sometimes we call this a single point of failure, SPOF. So this is a very big bottleneck in the internet industry. Why? Because we don't want this to happen. Why? Because most of the the breakthroughs happen through the means of communication. So the C1 wants to be communicated with the C2. So if the connection is not there, then what is the purpose of using the internet on all of this? So so this shouldn't happen every time. Excuse me. So this SPO should be avoided. So that's why what happened, then the internet, the cyberspace got developed into a more sophisticated thing, that is the distributed cyberspace, you can see. So here you can say multiple points exist, and the computers are connected here. Even though a single point of failure occurs, if the other servers are active, right? So they can help restore the connection, right? If the why? Because this, let's just say the C1 is connected, the C2 is connected. This both are connected to, let's just say this is the internet server, you can say. So if a single point SPF occurred here, a failure has been occurred here. So again, if the C1 wants to be communicating with this server, so it can establish its connection through this route. Earlier it used this route. Why? Because this is its nearest connection. So earlier it used this route, but here a crash occurred, a failure has been happened. So now this route is not available. So it will choose another route. So if this is also crashed, then it will go for another route. Okay. Here there is another issue. Sometimes what happens here is, if it's nearby servers get crashed, it will opt for a different and a longer one. So here what times here sometimes what happens, the loading times, they get increased. Yeah, can you hear now? Yeah, good. So here we have another smaller issue. What is that? The here what is happening? The loading times are getting more. So it's a better model than the centralized one. Here we are getting clarification for few bottlenecks, but few others are still present. So then later what happened? The cyberspace it got evolved to decentralized network. Here basically each individual has its own, you can say, like a own control unit. So basically, it's more spaced well. It's more decentralized in its way. So, do you know any examples for a decentralized network in our current internet era? Can you give me an example for a decentralized network? Like, do you know any medium that uses a decentralized platform? If yes, then please tell me. It's like, sorry guys. Have you guys ever heard of Bitcoin? You might have heard of Bitcoin, right? Like it's simple for everyone to understand. So yeah, Bitcoin. Why do you? What is the difference? You can say between a Bitcoin and a dollar. You can say, like, what is the main difference between a dollar, or you can say a rupee and a Bitcoin. So money is also like dollar is also available digitally, right? So Bitcoin is not just a digital currency. There's something much more to it. So what do you think it is there? Anyone? Yeah. Yeah, rupee works in India, dollar. Yeah, that is true. But I'm just talking about like the main difference between the concept of that money and the concept of Bitcoin. Yeah, the one major difference is like Bitcoin uses blockchain and all. So the main difference is, yes, Alex is right. So basically, for Bitcoin, there is no central bank. So for Indian rupee, there is a central bank called RBI. Similarly, for the US dollar, they have their own central bank called the Federal Bank. So basically, they control how the dollar value varies over the course of the years. So they hold the power. So they have the power to increase the dollar value or decrease the rupee value. So, but when coming back to the Bitcoin, there is no central bank. So everything is basically decentralized. So so everything is spread throughout the chain of network. So that is the another you can say some say that is a good thing, some say it's a bad thing. So that's the most arguable part. Uh, Having a central bank or not having a central bank, but that's not our discussion. So here we are just talking about how Bitcoin works, by using this blockchain technology and all. So how the whole the cryptocurrency is decentralized and all. So right now I can say, you can say that the blockchain, everything, is part of this decentralized system. So that's how the cyberspace has evolved over the course of years. So other example, if you want, another example, I can show you this. For example, if I go to this website, BGP tools. So what this website will tell me means, it will just show me the connections, like how my system, like I am right now accessing this website through a Chrome browser. So how I am connected to the internet through my laptop, through this Chrome browser, it is showing me. So for example, if I go to any, if IPv4 here, so it is showing me this is my IP and this is my AS name. So here AS is in nothing but autonomous system. So we will discuss these in the coming sessions. So here I'm just giving a small glimpse. So this is just my IP address. This is how I am connected to the internet. So it is just giving my autonomous system's name. And so this is the number that I'm connected, Bharati Airtel. So Airtel is my internet service provided provider, you can say. So you here, it will show me the different upstreams. So my Airtel service, uh, from India, I am located in Hyderabad, for example. So from Hyderabad, from India, it is getting connected to all of these different autonomous systems, AS1299. So they're from, this is operating through America, Hurricane, Italy, and America, another one America, so like this. So it is connected to all of these different autonomous systems. So for example, how an internet works is, if we consider, so let's just say this is America, right? This is US. So this is, you can say, this is Europe. This is Asia, for example. This is Australia. So in Asia, India, Hyderabad, and this is me. A. So let's just say I'm using YouTube or any other website. So you can say this is the internet. So similarly, each country we are connected to different autonomous systems. All of these are interconnected, right? So autonomous systems S1, S2, like this. So my autonomous system, the Bharat Airtel one, so is located here. Let's just say here. This is my autonomous system number. So here autonomous system, another one will be there. Singapore, you might say. Let's just say Singapore. Here the America autonomous system, America one will be there. So this is a part. So the whole thing is a decentralized network. So each network has its unique node. So each node has so many. So each autonomous system. So this 19222 autonomous system has various other connections. Okay. So again, these are connected to various other connections. So here, Hyderabad place, this location Hyderabad is there. In that city, in that area, my laptop is present. So it's part of my laptop is part of a very bigger autonomous systems network. But the whole network, as you can see, is decentralized, and generally all of us are connected through these autonomous systems only. So you can even after the session is done, you can even go to your Chrome and you can check this website, BGP tools. So it will show you how you are connected over the internet. So through which countries you are connected throughout the whole world, like how you are connected, you can map them. So that website shows you that. So that is about the, the decentralized cyberspace. So earlier it was standalone. Excuse me. Then server client, distributed model, decentralized model. So basically, now we use all of these. So whichever is best suited, we choose them. So, but basically, the thing is, we have right. We have the the best resources that are available. So if I have to, if I'm starting a new business, I will choose whatever the kind of technology that I would need, and I would deploy that. So as you can see, here this located in some other country, this located in some other place. So how we are connected means we are connected over the cyberspace through these routers and servers and all. So different networks, different routing networks, and different servers are available. And our data is getting encapsulated and decapsulated here. So for example, how this encapsulation works. So if you say, so we'll again let's just say the data here is generally traveled in packets. Okay, so we will deep dive into this data structures and all what are these packets and all. So here I'm just giving a small glimpse. So let's just say my data, let's just say I'm sending this message, hello world, hello, to my friend. So this message is traveled in the form of packets. So this is my data, right? So the data will be uh, stored here, and it will be first encapsulated before sending over to the internet. So what we can call this as, so basically what it is, encryption. So this is our data. So first what happens is, first the data gets encapsulated. So basically it gets encrypted, then a header will be added. So we basically call them IP headers. So what is this IP header and all? We will come to it. But you just understand I think you will understand this. So a header will be added. So now this will be sent to this router. Okay. So now again what happens is this gets encapsulated again. So first this information is gets encapsulated, and that new header will be added. And this data, so throughout until we reach y, our data that is present here, it will stay encrypted only, then only it will get decrypted at the point y. So in the middle, so in the middle, the way the data travel in the whole process, it will stay encapsulated only, it will stay encrypted only. So that's how our internet architecture has been built up, so in order to the safeguard the data. So you can say this is the simple understanding of an internet, how the data gets traveled from place A to place B, and how the data encapsulation and the decapsulation works. So you can simply, you can think of it as like a medical capsule. So the medical capsules that you know, we we use. So the outer layer is the one that is the encapsulated layer, and the medicine that is present inside that medical capsule. So that is our data. So in order for the medicine to not get spoiled, this external cover is applied, right? So similarly, in order for our data to not get stolen, or not get misused by somebody, we encapsulate the data, and then we attach the data with the respective headers, so with the respect to IP headers. So whoever is transferring our data, their respective you can say their respective DNA is imbibed, is just attached to it, and it is transported. So, and our data will always stay encrypted. So with, so through, that's why we can comfortably, we can safely share our information and communicate from anywhere with an internet connection. So that's how we basically the internet architecture operates. Is that clear, guys? Still no? Okay. So yeah, yesterday we already discussed about how the internet has evolved. So from human to human to World Wide Web to now how in the now we are in the IoT era. So the Internet of Things era. The how the speeds have also changed. So in the 80s, the 1G and then later 2G happened, 3G, 4G, and the 5G in the 20s, and now the 6G is expected to be around 2030. So that's how the basic understanding of internet and all. So now we are coming to the computer architecture and the OS part. So what constitutes a computer? Like what are the important aspects of a computer? What are the important parts? So we'll not be deep diving into each and every part. So we'll just be covering. So this is a you can say a simpler understanding of a computer that we might have seen generally. So it generally has an input device, an output device, so a CPU. So it has a logical unit, and and a memory and a storage. So this RAM, this space, 1 TB hard disks, so all of this. So this is our basic understanding of a computer. But mainly when when engineers, when they try to design a machine like this, so what were the main important key factors, you can say? So the main key factors are nothing are performance, efficiency, cost, and reliability. So they should perform good, and they should be efficient, and the cost to manufacture these, it shouldn't be too much, so it should be affordable for most of the consumers, and also they should be reliable, so they should stay for a longer period of time. So these are all the important key factors that the engineers has to uh, take note of. So based on these factors, they have developed these machines. So to develop these machines, earlier we need a certain set of an architecture. So similar to if you take an analogy to like in like constructing a building. So if we have to construct a building, we need a plan, we need a solid plan. So similarly, so in the earlier days in the 80s, when when all of this new technology is getting developed, we had these infrastructure set by few scientists, you can say. So we have these instruction set architecture, we have the micro architecture, we have this one human architecture. So our current laptops and our current systems are generally designed based upon this architecture. And then there is this Harvard architecture and generally a system design. So what are the things to keep in mind when we are trying to design a system? So generally the plan of action was like this. So everyone's perception was like this: there should be an input, there should be an output. So we should give an input, and the system has to do its thing, and it should give us an output. So that was the basic earlier understanding that everyone had. So there will be a central processing unit. So it has a few subunits present within it. So it has a control unit, it's a registry unit, and a logical unit, and a memory will be there. So each individual component has its its own things. So memory will handle the memory related tasks. So logic will and will gather the instructions from the input, and it will communicate with to the machine. So we'll be entering, so it will be communicating, it will be converting our instructions into binary code. Why? Because computers only understand this binary, so they only understand ones and zeros, right? So it the CPU, it converts our instructions, our input into, a language that can be understood by the computer, and then it will process the instructions, and then it will give us the output. So that was the basic architecture that everyone planned to build. So first, what was developed was this instruction set architecture. So what is this instruction set architecture? So generally there are two types of instruction sets that are there. So RISC and CISC. So reduced instruction set and complex instruction set. So for example, reduced instruction set means, in our day-to-day lives, for your clear understanding, ARM based chips. So you might have heard this name ARM. So have you heard this name? Yes, ARM is nothing but advanced RISC machines. So ARM is nothing but advanced RISC machines. So advanced reduced instruction set computers. So have you ever heard this word ARM based chips? These are the chips that we generally use in the mobiles and all. So the Apple is making its new chips, right? The M1 chips, M2 chips, M1 Pro, M2 Pro. So all of these chips are now based upon this ARM architecture. So this ARM is part of this RISC architecture. So reduced instruction sets. So this RISC is used in these ARM based machines. So like mobiles. So nowadays laptops are also there. So but earlier these Windows laptops. Windows means mostly these the Intel based laptops. So these the Intel based laptops that we had earlier, those are all come under the complex instruction set computers, CASC computers. The our mobile chips, the all of the mobile chips, the microprocessor chips, the very the small chips that we use in our day-to-day appliances, those are all come under the RISC bracket. That is the reduced instruction set. So basically, you can say, what is this ISA? It is in the name itself, instruction set architecture. It is nothing but it's basically what we are here trying to give is, we are basically giving a hardware support. Okay, we are giving hardware support for for managing all of these individual components. That is the memory, the fundamental features that are present, the input output model, so everything. So for the machine, for the individual components that are present inside the computer, for them to communicate thoroughly. Excuse. So this instruction sets help. So that is the main function of these instruction set architectures. So basically, they specify the behavior of the machine, you can say. So instruction set, microarchitecture, registers, and the combinational and other circuits. Like these are all part of the the whole. You can say the motherboard of the CPU. So next comes the microarchitecture. So what is this microarchitecture? So microarchitecture means, in simpler terms, if we go back to again to the industry analogy, for for a very large set of missions to work, small missions would always be aiding them, right? uh, for these to function, for these big machines to function, these small machines, they are needed, right? Similarly, in a big computer architecture, we need few simpler machines, that have a certain set of uh, line of work, like they only perform certain set of functions only. So They don't have the like an individual mind, and they're capable of doing multiple number of operations. They only do a certain set of operations, but they will definitely do those without any mistakes. So that is the micro architecture, you can say. So those are the built-in processes, so within the instruction set architecture. So these are the built-in process within the instruction set architecture. So for the bigger modules to work, so for the bigger units to work, we need these little micro architectures. So that's why the micro architecture aspect comes. So where are these used? So as I have said, these are basically used in the microprocessors and these microcontrollers. So for example, if you might have seen a motherboard of a CPU, right? So for example, if we Google the image, if you see here, so we know generally the important ones. So this is the main processor, and these are the memory lanes, storage lanes. So all of these are there. But what are these little things you see? So these are all these microcontrollers and these microprocessors. So all of these smaller ones. So we don't upgrade these things, right? We upgrade the chips, and we upgrade the memory and the storage components. We generally don't upgrade these components. Why? Because an update for these things is not necessary. Why? Because they are designed to do a specific set of tasks, and a regular update, we don't need to update them regularly. So these are all part of the micro architecture, you can say. All of these are these microcontrollers and the microprocessors, uh, the the Wi-Fi chips and all. So they also play another key role in the computer architecture, you can say. So instruction set architecture. So RISC and CISC. So RISC is mostly used by the mobiles, and mobiles and the small sensors. The fire sensors and all. You can think like the fire alarm sensors and all for the smaller appliances, and the complex instruction sets. So these are generally used in servers, supercomputers. You know. For these kinds of operations, a CISC type of computers are used, and to support these bigger components, a micro architecture has also been developed. Basically, what we can say from this architecture is nothing but these are basically a programming models. So these are the programming models of a processor, you can think like that. So based upon these architectures, the programming models have been built up. So that's why we are just having a quick understanding of each and everything about these things. So one human architecture. So our current our computers, these are all based upon this architecture. So it's the simpler one that we've been studying from our earlier days. So input output, it has a CPU. So it has this logic unit, a control unit, and a memory unit. So how each and every unit is communicated. So how each and every unit is, it has its unique set of functions. So here memory. So generally there are two types of memory. So here we have read and write memory for read and write instructions. So we will come to that. So what is this read and write memory? So where, that read and write is happening, and where the data is getting stored, where the data and instructions are stored in this memory. So everything, how uh, this is designed, this comes under the von Neumann architecture. So it just specifies how it's designed. Basically, each memory has multiple locations, and the contents in the memory are identified by the location. So everything happens in a sequential manner. So you can say it's like in a like a layered manner. So first this gets loaded up, then the second layer gets loaded up, then the third layer gets loaded up. So whatever the important components that are laid. So for example, similarly, you can like if you compare it to brick layering. So when in the construction, so to lay a brick, first you have to lay a batch of cement, and on top of it you place bricks, right? With a certain with a certain gap between them, and then again you place a certain amount of concrete, and then again on top of it another layer of concrete, right? And again on top of it you will place another brick. So it's basically a layered approach. So similarly, here also, uh, we the kernel, you can say, the system boots when the system is shut down, and when we turn on that button, right? When you switch on the turn on button, the system also boots in a sequential manner. It will load the important ones first, then the important ones that are located in its core layer, then it will move on into its other layers, the outer layers. So basically execution, it always occurs in a sequential manner. So that's the general way how the systems that are based upon this von Neumann architecture operates. And now there is another one, that is the Harvard architecture. So Harvard architecture is generally used in embedded systems. So what are embedded systems means? Similar to the micro architecture also, these embedded systems, they present inside the a larger operating system. So they have only a few set of instructions. So do and they will only operate upon those set of instructions only. So basically, generally they have two different memory units. So here, as you can see, instruction memory, data memory, control unit, and sometimes even the data is also stored inside the memory itself, memory chip itself. So that's why this type of architecture is only used in embedded systems. So here, separate memory block is needed, and data is accessed by one memory location, and instruction is accessed by different location. So it has data storage entirely contained within the CPU. So the amount of matter that you can store is also very less. Why? Because it's the part of the whole system. It's not like you are attaching. I'm attaching another 1 TB storage to it. It's not like that. It's part of this within the central processing unit. The data storage is also there. So that's why the systems that that employ this Harvard architecture, they always play a key role. It's like they're like an assist. They're assisting the bigger ones. So this architecture is helpful for making these kinds of machines which have a defined set of instructions. So do they will only operate upon this a particular certain set. So they will not deviate. So for these type of components, we use this Harvard architecture. And also to scale in in bigger devices, it's tough. Why? Because it's also a very complex design. So that's why it's generally used in the embedded systems. And system design. So basically, coming to the system design is nothing but like how, what are the excuse me, points, what are the requirements that are there, like the architecture, what is the module, what are the interfaces, and what is the data. So basically, it contains all of the necessary information, the design requirements that we would be needing to build an end product. So that constitutes to the system design. So it has sometimes modular systems. So if we want to upgrade only a certain component of it, we can upgrade only a certain component of it. So similarly to the example, the motherboard example that I have showed there, if I want to upgrade my RAM, I would be upgrading only my RAM. I don't have to change my whole motherboard, right? So basically, you can think of it like a modular system. So it has been designed like that. Why? It so everything will be there. The efficiency will be better. The cost will be less. Why? Because I don't have to change the whole motherboard. I just have to change a single component, the RAM component. So there are these many uh, better points. So that's why these modular systems are developed. So that comes under the system design, the design aspect of it. So coming to the hardware, so as you can see, these are our the most common ones. So the RAM, ROM, the type of the disk drives, the storage, and the CPU. So all of these are the common ones. The connected, this is the connection cable, Ethernet, so like this. So it has a motherboard and motherboard form factors. So depending upon the the size of the CPU that you will be using, the form factor will vary. So if the CPU size is more, it can accommodate more RAM. So it can accommodate more slots. Also, it can accommodate more drives. So like that. So based upon the form factor, different sizes of motherboards are there. So and there are also different types of RAM. So random access memory and read-only memory. So PROM means permanent read-only memory. E means erasable permanent read-only memory. So these are, as technology, as time has advanced, so different types of memory devices have popped up. And storage devices, so there are different types: auxiliary storages, floppy disks, CDs, hard disks, DVDs, Blu-rays, SSDs. So these are the current gen, the new gen one. So all of these are all the main components of the computer hardware. So there are so many other components also, the microcontrollers and all, microprocessors, the microcontrollers. So we generally don't upgrade them. So that's why we generally upgrade these aspects of a motherboard. So that's why we have included these. So just before deep diving into this, is that clear until now, guys? Like how the architecture has been built, set up, and how the systems have been evolved by using this. So this is how. So now we have arrived at the hardware component. So now here what happens is, here we will be just discussing how the Windows operating system, the Linux operating system has been built up. So now we are at the hardware level, at the motherboard level. So from here onwards, we will be going in a layered way. So on top of hardware, what happens? Then what happens and all. So until now, is it clear? Just if you have any doubts, you can. Yeah, yeah, we will be coming to that. Right. So if you are coming back to the RAM, so we have this random access memory, the read-only memory. So each has its distinct functions. So CPU registers in the cache. So basically when you're coming to the memory, there are two parts of it: volatile memory and non-volatile memory. So for example, if you're in a laptop, if I shut down my computer and if I again log back in, so whatever the data that is present in my laptop, it's not it's go it is staying there only. It's not going to get deleted. But uh, let's just say I have shut down, I have opened few tabs in my Chrome browser. So without closing those tabs only, I have shut down my laptop. But once I again restarted my laptop, after I opened it, when I check, the Chrome is not open. Okay, it is closed automatically. So whenever I shut down and restart my laptop, all of the memory that is there in these applications, it gets deleted. So the laptop, it doesn't store the data in its RAM. So you can say that RAM is a volatile memory. So what happens is, immediately whenever the power gets cuts off, the memory gets deleted. So that's why whenever the power gets switched on, the processor will reassign the memory. So whenever I open Chrome, so immediately, let's just say for example, I have 8 GB of RAM on my laptop, in my laptop. So whenever I open Chrome browser, the processor knows that, okay, the user has opened Chrome browser, so I have to allot this x amount of memory. So let's just say it allots 1 GB of memory. So let's just say my laptop configuration is 8 GB of RAM and 512 GB of storage, right? So whenever I open the Chrome, it will allot that 1 GB from this RAM. Okay, the Chrome app that I have downloaded, right? It is stored in my storage space. So it is stored here. That 8 will be. So in order to use the Chrome app, I need this RAM memory. So whenever I open, I have already opened two tabs. If I open another tab, so it let's just say the tab requires another 200 MB. So again, it will take from my RAM. So like that. So whenever I switch off my system, the whole uh, RAM that is there, 8 GB and whatever that is allocated, it gets deleted. Okay, but the storage that is there, it stays there only. My Chrome app stays there, stays in my laptop. Only the memory, whatever that I have used, it gets deleted. It gets deleted means it gets closed. The history and everything, it gets stored only. So that's the simple difference between a RAM and ROM. So volatile and non-volatile memory. So there are different types of RAM: DRAM and SRAM. So DRAM means dynamic RAM and SRAM means static RAM. So what are the main characteristics of the storage devices? So the main thing will be, they should have a lot of speed, they should be volatile, and access method, the portability, the cost and capacity. So whenever companies are trying to develop a new storage device, they should think about these characteristics. Why? Because these are the most important ones. So coming back to the storage, so bits and bytes. So you might have heard of this. So one bit is nothing but it's just a single value, zero or a one. So either one bit can take either a zero or a one. So 8 bits consist of one byte. So if we combine 8 bits, it will give us 1 byte. So similarly, millisecond, microsecond, nanosecond, just a simpler. Just in future, we'd be needing these milliseconds. And the measurements, byte, 4 bytes are called nibble. 8 bits is a byte. So then we'd be moving on to the kilobytes, megabytes, gigabytes, terabytes, petabytes. So the storage, you might have heard all of these names. So motherboard form factors. So like see, as you can see here, this is a smaller motherboard, then this is a very bigger one. You can see the difference between the number of lanes and the storage lanes that each motherboard having. Here it has, this has more lanes, and the chip that it is using is more powerful than the one that it has here. So that's why to accommodate this and to power this chip also, a bigger form factor is required. And this is the fan, and these are the RAM lanes and storage lanes. So these are all the other microprocessors and the microcontrollers. So everything. So based upon the type of form factor, like the kind of workload that you are doing, you would be choosing these different types of motherboards. So this is how RAM has evolved over the years. So this is the RAM area and this is the storage part. How memory has evolved. So earlier we have these HDDs. So you can read upon these SSDs, compact discs, flash drives, and in the when you come to the RAM part, ROM, RAM, non-volatile and volatile. So what is this RAM? So SRAM and DRAM. So all of these static RAM and dynamic RAM. So now we are in this DDR4 era. So every time when you try to buy any, a RAM for a motherboard, so you would be seeing these kinds of names: DDR4 SDR RAM. So DDR4 SDR RAM means nothing but double date rate, double date rate, synchronous RAM, synchronous dynamic RAM, double date rate, synchronous dynamic RAM. So this is the new gen RAM that right now we are using. So over the course of years, RAM and ROM and the external storage devices have evolved. So earlier we have these beta disks. Then we have moved on to the SATA SSDs, SATA disks, SCSI, and then the SSD, solid state drive. Next, coming in, this is a RAID. RAID is nothing but redundant array of independent disks. So this is mostly, this type of setup is mostly used in servers. So servers, various RAID models are there. So RAID 1, RAID 2 configuration, RAID 3 configuration, like that. So what is this RAID configuration means? Nothing but they are they're splitting the blocks into different types, like striping and mirroring, stripping and mirroring. So what is happening here means, if you want to, so let's just say my laptop, I want to backup my data. Let's just say company is there. It has, let's just say, hundreds of computers inside the office, and all of their data is connected to a server. So, and also if they want to back up the data, or sometimes an error occurred, or if they want to just want to get the data from one place to another computer. So if the whole data, if it is stored in the server, right, and all of these employees would be getting their data and exchanging their data with the servers, with the medium of servers, right? So in these servers, the data disks are stored in different RAID patterns. So what they use is they use these techniques called striping and mirroring. So what is this striping mirroring means? Let's just say this is my data block. So it has 1, 2, 3, 4, right? Let's just say I'm splitting my data block into 4 parts, for example. So this is my data block. So what happens is in this server, first I will copy my data block as it is. So 1, 2, 3, 4. So 1, 2, 3, 4. Another way of saving this data is I will just split this data into alternate forms. So I will split the data into one, it's like this, 1357 and 2468. Okay. So I will again mirror this 1357. So I have this is one device. This is my backup one. This two is backup of disk one. And similarly, the other half of the data that is here, 2468. And again, I am creating a mirror for this disk 4. So why disk 2 and disk 4? These are for fault tolerance. Fault tolerance means if this disk 1 gets crashed, immediately uh, it's the rate it switches to disk 2. The data transfer switches to disk 2. So that what happens? The time will be avoided, right? So a lot of time gets saved. So this is one formation of RAID 0. So similarly, RAID 1, RAID 2, RAID 3, different types of formations exist. So here what it is doing is, here it is first splitting the data and arranging it in two different blocks, two different disks. And again, we are mirroring these disks. So we are striping, we are stripping the disk, and we are also mirroring the disks. Both of them are happening. Sometimes we only mirror the disks. Mirroring the disk means only like here 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 1, 2, 3, 4 gets mirrored, and 5, 6, 7, 8, 5, 6, 7, 8. They get mirrored. 5, 6, 7, 8. So this is another RAID configuration. This is another RAID configuration. So like that we store the data in these different how this is how the data gets saved in the servers, you can say. So what are the ways that they employ? Striping is one thing and mirroring is another one. The parity is nothing but it's basically a checksum. So basically, to check whether the data that has been saved is correct or not, they will add another parity check. So we use this parity in the networking part also in the coming sessions. So here this parity is also included some cases. So it's nothing but what? It's just a calculated value used to mathematically rebuild the data. So if the data gets lost or if the data is correct or not, so in order to check all of these things, we sometimes do a parity check. Parity disk is also there. So firmware. So what is firmware? Firmware is nothing but the software that is encoded on in the hardware, in the chips that we have discussed, and also the firmware it is present in the computers, printers, and all. So what is the firmware? Means the BIOS. BIOS means the basic output system of a computer. So it is present on the motherboard, related to the mother. So we will discuss these things that is related to the BIOS and all in the tomorrow session, and then we'll move on to the cyber security part, to the networking part. So is that clear, everyone? Until now, like if you have any questions, you can ask me. Yes, you will have the recorded videos, George. If you can scroll up, you can see a WhatsApp group, and the video has been posted. If you don't have any questions, then we can end the session, guys.